You ever wonder why a rubber band snaps right back, but when you bend a paperclip, it just stays bent? It seems simple, but it's all about elasticity. And today, we're going to get right into the science of why things stretch, why they deform, and how they find their way back.
All right, so here's our game plan. First, we'll nail down what elasticity even is. Then, we'll learn the lingo engineers use, stress and strain. After that, we'll peek into the lab to see how materials are actually tested. And this is a big one. We'll see why the shape of the test piece is so darn important. Finally, we'll see how it all comes together with some surprisingly simple geometry.
So, let's start at the beginning. What are we really talking about with elasticity? Well, you can think of it as the science of bounciness. It's a material's built-in desire to fight back against being distorted and to spring back to its original shape the second you let it go. And this simple question, it gets to the absolute core of it all. The big difference here is how these two materials handle the internal forces we put on them. The rubber band, it's just hanging out in its happy place, its elastic zone. But that poor paperclip, we've pushed it too far, beyond its elastic limit, into what's called plastic deformation. It's permanently changed. Now, to really get a grip on this stuff, we need to speak the language. And in the world of material science, that language is built on two absolutely fundamental concepts: stress and strain. The whole field that covers this is called continuum mechanics. Now, that sounds super fancy, I know, but the core idea is actually pretty straightforward. It lets us ignore the trillions of individual atoms and instead treat a solid object like one single continuous thing. Trust me, it makes the math way, way easier and lets us predict what's going to happen. And this picture here is the perfect way to visualize it. Just imagine the material is made up of this perfect grid. When you pull on it or push on it, that grid gets all distorted. Continuum mechanics is basically the toolkit we use to figure out what's happening at every single point on that stretched out grid. Okay, so inside that grid, we're tracking our two key players. First, you've got stress. That's sigma, which is the internal force fighting back, all spread out over an area. You can think of it like internal pressure. And then you have strain. That's epsilon, which is just a measure of how much the material has actually stretched compared to its original size. They're really just two sides of the same coin. You apply a stress and you get a strain. So why are we getting so into the weeds with these definitions? Well, because they are the building blocks for literally everything else. They're the core of Hooke's law, which is the rule that describes that snapback behavior. They're critical for figuring out why things break down at the atomic level. And they're even how we understand the way we permanently shape metal to build cars and planes. So we've got the theory down. Awesome. But how do we go from these ideas on a whiteboard to actual numbers we can use? For that, we've got to leave the classroom and head into the lab to put these materials through their paces.
And what's so cool about this is seeing all the different ways we can, well, torture materials for science. We can pull on them, that's tension, or squeeze them in compression. We can poke them to test their surface hardness. We can bend them to see how they flex, or we can even twist them, which is called torsion. Each one of these tests tells us something unique about the material's personality. Now, to make sure the results we get from all this pulling and twisting are actually useful, there's something that's way more important than you might think: the exact shape of the piece of material we're testing. Yeah, we don't just grab any old chunk of metal. These test specimens are precisely engineered for a reason. The smooth, general ones give us a baseline for the material's strength. The notched ones are designed to focus all the stress in one tiny spot so we can study how failures start. And the pre-cracked ones, those are for the really advanced stuff, looking at how cracks actually grow. And the reason for all this fuss is one simple, powerful word: consistency. When everyone, everywhere, uses the exact same shapes, the geometry of the part is no longer a variable. This is like the secret sauce of modern engineering. It means a designer in Seoul can confidently use data from a lab in Berlin and know, for sure, that the part will behave exactly as planned. Let's zero in on the most common one, the classic dog bone tensile specimen. See how it gets thinner in the middle? That's called the reduced section, and it's designed to make absolutely sure that all the action, all the stretching, happens right there, where we can measure it accurately. And that specific area we measure is called the gauge length. And look, this isn't just a friendly suggestion. We're talking about a global standard here. Big organizations like ASTM in the US, EN in Europe, and KS in Korea, they all publish incredibly detailed rules for these specimens. It ensures that everyone in the world of materials science is literally speaking the same language. Okay, so let's get to the payoff. This is where all that groundwork starts to come together. Because with this standardized approach, we uncover some beautifully simple and totally predictable rules for how things stretch. Let me ask you a quick question. Let's say you have two elastic rods, same material, same thickness, but one is twice as long as the other. Now, if you pull on both of them with the exact same force, which one do you think is going to stretch more? It's a bit of a trick question, but the answer is the longer one. And it's not just a little more. If you double the length, you exactly double the amount it stretches. The relationship is perfectly linear. It kind of makes sense, right? More material along the pole means more stuff is available to stretch out.
All right, round two. Let's switch it up. What if the rods are the same length, but one is twice as thick? It has double the cross-sectional area. We pull with that same force. What happens to the stretch now? This time, it's the exact opposite. By doubling the area, you've essentially made the rod twice as tough, twice as resistant to being stretched. So the total amount of stretch gets cut exactly in half. This isn't just some neat coincidence. It's the elegant, predictable code that's written into the behavior of elastic materials. This scaling, directly with length and inversely with area, is the mathematical bedrock that allows engineers to design everything with incredible confidence. It means the same rules that apply to a tiny little wire on a circuit board also apply to the massive steel beams holding up a skyscraper. The physics just scales. So we've spent all this time in the neat, tidy, and predictable world of elasticity, where things always bounce back. But what happens when you pull so hard that they don't? What happens when you push a material past its point of no return? Well, that's where things get really interesting. And it's a story for another time.